Huh. I'll look for it. Okay, so we're going to do, so now we're dealing with anybody have any homework questions, first of all? Did I assign any homework yet?
No.
Okay, today I will assign homework. So, yeah.
You sure? You don't have to. No, thank you. I like my degrees.
Rather than a holiday Friday.
Yeah, that's right. Okay, so this is the kind of thing you're going to have to do in the homework. So you have an ideal Rankine cycle. That's the only kind we've talked about so far. Ideal means that there's no superheat process and there's no reheat process. So that's the kind that we've dealt with so far. And water is the working fluid. A saturated vapor enters the turbine. At 8.0 megapascals. And saturated liquid exits the condenser at 0.008 megapascals. The net power output of this cycle is 100 megawatts. And we want to calculate the efficiency. The back work ratio. Anyone remember what that is? That's the ratio of the work you have to put into the pump to the work you get out of the turbine. C, the mass flow rate. D, we're just going to basically go through all the stuff you can calculate. The rate of heat going into the system at the boiler. E, the rate of heat leaving the system at the condenser. And F, if the cooling water inlet temperature is 15 degrees Celsius and the exit temperature is 35 degrees Celsius. What's the mass flow rate of the cooling water? Yeah. So the first impression of this problem is it's kind of shocking with how little information you're given that you can get all this calculate all this information out of it. Remember, we're making a few assumptions that that make it so you need a lot less information to be able to do these calculations. We have, I guess, 2 of our states are saturation states, which means you only need one property. So that's That's why we only need the pressures at these two states, because we have saturation states. And then remember that the turbine is isentropic and the pump is isentropic. So we know that the entropies, the specific entropies at the beginning and end of those two are going to be the same. And then we know that the pressure is constant through the condenser and the pressure is constant through the boiler. So that's a lot of stuff. And so I'm going to kind of write this out like, I don't know if you've ever done a standardized test, like a logic type test, where you have to write out tables and stuff. But I'm going to kind of put everything out in a form where we can start to sort through what we know, and then we can start to calculate the stuff. All right, so here's state, well, first let me draw the picture. I think it's always helpful to have that. This is the ideal Rankine cycle, so it always looks the same. This is 2, 3, and 4. So at state 1, that's going, this is the turbine, this is the condenser, this is the pump, and this is the boiler. So state 1, going into the turbine, we know that entering the turbine, the pressure, okay, we know it's saturated. We know that the pressure is 8 megapascals. What?
Wasn't it 80?
Yeah.
8.0, I think. 80, you're right. I think I might have written it down wrong. It should be 8.0.
Okay.
Sorry about that. And then, since this is a saturation state and we have the pressure, we can look up any property we want in the table. Okay, so that means that the specific entropy, is something we have that. Okay, state 2. So this is the isentropic turbine. At state 2, what do we know? We know that it's in the vapor dome, so it's a saturated mix. We don't know what the quality is of that mix. We are given the pressure as the liquid exits the condenser. But remember, the condenser is constant pressure. So the pressure as the liquid exits the condenser is the same as the pressure going into the condenser. Okay? So state 2 is where it's going into the condenser. So we know that the pressure is 0.008 megapascals. And we know, because it's an isentropic process, that S2 is equal to S1. Well, since it's saturated and we know the pressure, we can look up anything we want in the table. So from this, can you see how we could get the quality? I mean, we're probably going to need the quality to do calculations. If we know the saturation and we know the pressure, we can look up the specific entropy for a liquid and a vapor, and then use what we know to be the actual entropy to calculate that quality. And then we can calculate anything else we need. I didn't say this at the start, but basically, like, what are we trying to find? Like, do you remember that from our calculations of efficiency and bath work ratio? And basically, if we know the specific enthalpies at all four of these states, then from there we can kind of calculate everything. Okay? Now state 3. What's happening from 2 to 3? This is a isobaric condenser. This is a saturated liquid. Since this is a constant pressure process, we know that P3 is equal to P2, so we have that. Since it's saturated and it's all liquid and we have the pressure, we can look up anything we want in the table. And then the last one at state 4. This is the only state where it's not at saturation. We have one that's a mix, but this is the only one that's not at saturation. So this is a compressed liquid, which makes it a little bit more of a hassle because we need 2 properties in order to look this up. But this is an isentropic pump. Well, we know that the entropy at state 4 is the same as the entropy at state 3. We also know that through this whole process, through the pump, this is a liquid, which means we can treat this process as incompressible. Okay, so we can't look anything up in the table for this yet, but we have stuff to work with. And then the last one, state 4 to state 1. That is an isobaric boiler. Well, if that process from 4 to 1 is isobaric and we're given the pressure at state 1, then we know this also. So P4 is equal to P1. Okay, so now we're going to go around and just try to figure out the specific enthalpies at each of these things. Before I even think about what I'm trying to calculate, I'm just going to try to calculate those enthalpies. Okay, so at state 1, you can just use the table for a saturated vapor. And you get that H1 is equal to 2758 times 10 to the third. This is in joules per kilogram. And you can also, since you can see that these entropies are going to be important, we might as well look up the specific entropy here too. So 5.7432 times 10 to the third joules per kilogram Kelvin. And now we'll go down to state 2. Well, for state 2, the key to being able to look anything up is knowing the quality. Are you with me on that? S2 is equal to S1, so that's 5.7432 times 10 to the third. And we know that it's in saturation, and we know the pressure, so we can look up that the specific entropy for the gas is 8.2287 times 10 to the third. And the specific entropy for the liquid is 0.5926 times 10 to the third. And so we can set up an equation, 5.7432 times 10 to the third is equal to X times the specific entropy for the gas, plus 1 minus X times the specific entropy for the liquid, from that, you can calculate that the quality is 0.6745. So what percentage of this water is steam?
67.
Yeah, 67%. Yep. Well, now that we have that, we can use that to calculate the specific enthalpy, which is what we're looking for. The table says that H for the gas is 2577 times 10 to the third, and H for the liquid is 173.88 times 10 to the third. So H2 is equal to 0.6745 times Hg plus 1 minus this times HL. And so H at state 2 is 1795 times 10 to the third. And this is joules per kilogram. What? Okay. So state 3 this is a saturated liquid. We know the pressure, so we can just look this up directly. P3 is equal to 0.008 megapascals. And so the table just directly tells us that H3 is equal to 173.88 times 10 to the third joules per kilogram. But now we have the one that's always going to be kind of the biggest hassle, because it's the only one that's not at a saturation. And all we know about it is the pressure. We do know the pressure. We do know the entropy too. And we know it's an incompressible material going from state 3 to state 2. So always keep your eye out for chances to use that. Okay, so state 4. This is a compressed liquid. We know the pressure, but that's not enough. Okay, well, is there anything we can use about the fact that this is incompressible? Remember that we know so if you go back to our definitions of the energy transfer for the different stages, this is the pump. And at the pump, we know that W dot for the pump divided by M dot is equal to H4 minus H3. And if you assume that it's incompressible, we also know that this is equal to the specific volume times the pressure at state 4 minus the pressure at state 3. Okay, so we know H3, we know the specific volume, we know the pressures at state the pressure at state 3, and just making sure that's isentropic. Oh, okay. So what?
You use entropy.
Yeah, well, we know that this is the same as the pressure at state 1. And we know that this, oh, so I wrote this down wrong. That's where my mistake was. P4 is equal to P1, not P3. Okay, so it's 8 megapascals. And so H4 is just going to be equal to the specific volume. I'll use 0.001 times 8 times 10 to the 6 minus the pressure at 3, 0.008 times 10 to the 6. And so H plus H3. I'm just, rearranging this equation. So H4 is equal to 181,872. And that's in joules per kilogram. So now we have the specific enthalpies at each one of those states. Now pretty much we can just go through and answer these. The first thing we want is the efficiency. The efficiency is equal to 1 minus H2 minus H3 over H1 minus H4. So that's 1 minus, just plug these in, 1795 times 10 to the third minus 174 times 10 to the third divided by 2758 times 10 to the third minus 182 times 10 to the third. And you get an efficiency of 0.371.
So is that efficiency the closer you are to what, the better it is?
The closer you are to 1, the better.
So this sucks.
Well, remember that the way to get a realistic measure of how much it sucks is to figure out the temperatures at the boiler and the condenser, because you're limited by what you can, by your temperatures at those two things. So, like, do we have the ability to calculate that? At the boiler, we know the pressure coming out of the boiler. I guess we can calculate, just look up the temperature at state 1. We can just look up the temperature at state 3, use that to calculate the ideal efficiency, and then you'd get a more realistic sense of whether this is working well or not, Okay, so part B, what are we looking for? Back work ratio. So the back work ratio is W dot over M dot at the pump divided by W dot over M dot at the turbine. And if you go back to our definitions of the different stages, this is H1 minus H2 divided by, I did the one on the turbine. For the pump, it's H4 minus H3. For the turbine, it's H1 minus H2. And so you can plug those in. You can see, since these are all enthalpies, and I'm representing all these times 10 to the third, those will all cancel out. So I'm going to rewrite this as like 182 minus 174 divided by 2758 minus 1795. And so we get a back work rate of 0.00831. Well, that tells you that you're using less than 1% of the energy you get out of the turbine to run the pump. Okay, you want that to be as small as possible. Now, the mass flow rate. How are we going to get the mass flow rate?
We're given the work.
We were given the the net power. Okay, so we want the mass flow rate. We know that the net power, which is the rate of work done at the turbine minus the rate of work done at the pump, is equal to 100 megawatts. So that's equal to 100 times 10 to the 6. We know that W dot for the turbine over M dot is equal to H1 minus H2 and so that was, what was our H? Okay, so that's 2758 times 10 to the third minus 1795 times 10 to the third. And so that's 963 times 10 to the third. And we know that WP dot over M dot is equal to H4 minus H3, which is 181,872 minus 173,880, and that is 7.99 times 10 to the third. So WT over M dot minus WP dot over M dot is 963 times 10 to the third minus 7.99 times 10 to the third. And so WT dot minus WP dot is equal to, if you subtract these, you get 955.01 times 10 to the third. And so this is 955.01 times 10 to the third times M dot. And this is equal to 100 times 10 to the sixth. So M dot is 100 times 10 to the sixth divided by 955.01 times 10 to the third. And what do you get for that? Anybody? 100 E6 divided by 955 E3. So 104.7 kilograms per second. That's a lot of stuff.
Now that pump doesn't suck.
Yeah. Let's see. So now we want the heat transfer at the boiler and the heat transfer at the condenser. So let's do the boiler first. We know that, we can just go straight back to those, the things that we get out of the first law for control volumes. It says that at the boiler, I didn't write that down for some reason, but let's see, the boiler is from state 4 to state 1. You have something like Q dot minus W dot plus M at times H at 1 minus H at 4. And so Q dot over M dot is equal to H4 minus H1. I have these backwards. It's inlet minus exit. So the exit is 1, the inlet is 4. The sign convention of the boiler matches the sign convention of the first law. So we have that Q dot over M dot for the boiler is H1 minus H4. And that is 2758 times 10 to the third minus 181,872. So that's 2.576 times 10 to the 6. So Q dot for the boiler is the mass flow rate times this. So 104.7 times 2.576 times 10 to the 6. And you get 2.6.70 times 10 to the 8. And this is in watts. Then at the condenser, Q dot over M dot is equal to H2 minus H3. The sign convention for the condenser, remember the heat for the condenser is coming out of the system. So that's the opposite of the first law sign convention. So we have Q C dot over M dot is equal to, I don't even have to do this because I'm sorry, I just already read this off. I'm doing something I don't need to do there. So what?
It's an ideal system. Couldn't we also use the change in Q is going to be the change in W?
Well, no, because energy is added and removed by power also. You know what I mean? Well, we could.
Net change.
Yeah.
W net, it should be equal to
U delta Q, right? If it's an ideal system. No loss.
W net, W dot net is equal to Q dot net.
QB dot minus QC dot.
Right, that's what yes, that's right. So we could do it that way too, yep. But it's not just gonna be, it's not just like the heat that comes in goes out of the condenser.
Yeah.
Okay, so here we got, H. Okay, so this is 1795 times 10 to the third minus 173.88 times 10 to the third. And so Q dot for the condenser, multiply it by M dot, and you get 170 or 1.70 times 10 to the eighth. So the difference there is the net work. Okay, so now the last one is the cooling water, I think. So the first law, we're doing this thing where we treat the condenser as a system, and we have the working fluid going from state 2 to state 3, and then we have the cooling water going this way. And this is the inlet and this is the exit of the cooling water. We're assuming this is steady state. So I'm going to just write out a simplified form of the first law for control volume. So we got 0 is equal to, remember there's no heat transfer except between the system. So there's no Q dot. There's no W dot. So this is just equal to the mass flow rate of the working fluid times H at the inlet, that's 2, minus H3, plus the mass flow rate of the cooling water times H at the inlet minus H at the exit. This stuff, we know all of that. The cooling water, we know is incompressible. Okay, so the change in specific enthalpy for the cooling water is equal to the change in specific internal energy plus the change in pressure times specific volume. The condenser, we're assuming that it's for the cooling water and for the working fluid, we're assuming that this is constant pressure. It's incompressible, so this whole thing goes away. So the change in specific enthalpy of the cooling water is equal to the specific heat of the cooling water times the change in temperatures. And that is 4186 times, we were given that the cooling water comes out at 35 degrees Celsius and goes in at 15. So this is $83,720. We calculated this before just a second ago, didn't we? H2 minus H3. So it's that times the mass flow rate. So 1.7 times 10 to the 8th. So 0 is equal to 1.70 times 10 to the 8th plus m dot for the cooling water times 83,720. How did I get this sign backwards? Oh, this should be negative because this is the change in the specific enthalpy of the cooling water, which is exit minus inlet. And so we get that m dot for the cooling water is 2,030 kilograms per second.
It's a lot of flow.
Yeah, that's a lot. Yeah, it's like a morning brain workout. But anyways, it's easier if you're not sitting in front of people trying to, but it's really not that hard. It's just like bouncing around from what you know to what you know. Remember that the first thing you want to do is calculate the specific enthalpies at each one of those 4 states. Once you have that, most of everything else sort of falls into place. Anybody have any questions about that? Okay, that's all.